Hey, in previous videos we talked about how ionic compounds tend to be brittle and they shatter easily. We also said they form lattice structures. Well, metals tend to form lattice structures as well, but they don't tend to shatter. They dent. Why is that? Well, today we're going to talk about metallic bonding. Let's get started. Just like ionic compounds, metals have attractive forces between particles of unlike charges. And metals do form lattice structures much like ionic compounds. However, it's how they treat their electrons that we find the difference. Previously, we showed how ionic compounds will have a series of positive and negative ions in the lattice structure. A metal does something a little bit different. Now, they don't really lose their electrons and they don't really share them either. However, the outer energy levels of these metal atoms tend to overlap. So their valence electrons then form what we call a sea of electrons. In doing so, this sea of electrons surrounds these metal cations in the lattice. We say that these electrons are delocalized. Simply put, that they're not being held by any one particular atom. So they're free to move throughout that metallic solid. But there's still that attractive force between the cations and the electrons. The electrons holding the cations together in this lattice formation. So a metallic bond then is that attractive force between the metal cations and those delocalized electrons. Now the melting points of metals can vary somewhat. You have ones like mercury that are liquids at room temperature. Then you have others like tungsten that have a melting point of about 3,400 degrees Celsius. But in general, we say that the melting points and boiling points of metals are fairly high. Since those cations and electrons are somewhat mobile in the metal, the melting points aren't quite as extreme as the boiling points are. However, to make boiling occur, you have to separate atoms. So in a boiling situation, an enormous amount of energy has to be given in order for those atoms to be separated, translating to a very high boiling point. You probably noticed that earlier I put the hammer to this canister lid, and you can see how it's dented the lid. What makes metallic bonding different in that these things dent instead of shatter? Whereas before we showed that ionic compounds shatter because the repositioning causes like charged particles to be next to each other, thus forming repulsive forces, metals have something different that happens. In the case of a metal, when I provide a force, even though it's moving the cations, those delocalized electrons are allowed to flow around the cations, still keeping them in a lattice formation. Because of that, we say that metals are malleable. It just means they can be hammered into sheets. They're also ductile, which means they can be drawn into wires. So again, the particles in a metal are somewhat mobile, allowing them to be pulled or pushed past one another. Those delocalized electrons also cause a metal to have extremely good conductivity when it comes to electricity and heat. Since those electrons are allowed to flow, it allows for the flow of electric current. And delocalized electrons allow heat to be transferred from one place to another much more easily. Those delocalized electrons also allow for the interaction of light, absorbing and releasing photons so that we have what we call luster. We also see that the more electrons that are available to form this sea of electrons, the stronger the metal will be. That's why a lot of transition metals have extraordinary hardness, because they have not only the s electrons available to them, but also the d electrons as well. Some of these transition metals are extremely strong, like vanadium and chromium, for example. Because of the nature of metallic bonds, it's actually easy to introduce another element into that metallic lattice. We call this an alloy. An alloy is simply a mixture of elements that has metallic properties. Some of the most common alloys are stainless steel. Remember brass from our gold penny experiment? That's a type of alloy. And as you might guess, the properties of alloys will be a little different from the elements that form them. It may allow for increased strength or better heating and electrical properties. As we close, let's talk about two types of alloys. One is called a substitutional alloy. That's when you have some of the atoms in that original metallic solid being replaced by atoms of a different element. The second type is what we call an interstitial alloy. That's when we introduce smaller atoms in those little spaces between the metallic cations in that metal. Carbon steel is an example of an interstitial alloy. Spaces in that iron matrix allow for the introduction of carbon, and that actually changes the physical properties of the iron. It allows for that solid to be harder and stronger. We use alloys every day. They're used commercially and they're very important in our day-to-day life. And that's the end of our time for today. Today we talked about metallic bonding, how we have these metal cations in a matrix surrounded by a sea of valence electrons. We discussed the properties of metals such as their ability to conduct electricity and heat, their malleability and their ductility, and how it relates to the sea of electrons that we see in that metallic structure. Finally, we discussed alloys for just a few minutes, giving definitions of substitutional alloys as well as interstitial alloys. Look at that, you've wrapped up another chapter. Great job. I hope it's going well for you, and if I can help you in any way, let me know. Until next time, God bless.